So this is the last part of this section, which is a mixture of lecture and lab, and it's called polarized filters. And I have two polarized filters, and I'll share with you what these guys can do. Well, polar, something that is polar has like a north pole and a south pole. We talked about polar molecules in chemistry, poles with magnetic fields, opposite ends. And these polarized filters are made with a very special polymer, and these polymers are all aligned in the same direction. I'm going to try to draw this three-dimensionally. So I'm going to draw this first filter like this. And imagine that these polymers are all aligned in this orientation like this. Okay, so this is a representation of the long chain polymer molecules. Remember polymers from chemistry. Poly means many, mer means unit. These are many units long. They're very, very long. And light that's coming from the outside, coming in from the window, this is light that is called scattered. It's not polarized. So I'm going to try to draw a light in the distance. So here is the sunlight, okay? Actually, it could also be the light from this room. But if you remember, light has properties of both a particle and a wave. And so what's happening is that these particles are traveling in, or these waves are traveling in the up and down direction like this. This is kind of traveling up and down towards this filter. But they're also traveling left and right like this. They're also traveling at angles going like this, and every angle in the 360 degrees that we can see here. So they're going off like this as well, okay? So this is called scattered light. Okay, so here's our scattered light. And this scattered light is composed up of waves in all 360 degrees. Okay, in every which direction, up and down, left and right, angles in every different direction. What happens though is that this filter right here is going to be blocking the light waves that are in every other direction except for the up and down. So what's going to happen is that this is going to allow the passage of the up and down waves like this. Okay, now imagine you have a prison or a jail cell, and the bars are in the up and down orientation. And the prisoner says, hey, I need a broom. You know, who knows, the prisoner may want to clean a cell. And, well, how do you pass that broom, okay? If you take the broom and you try to pass it, boom, like this, all the bars of the jail are going to block that broom. How do you pass the broom to the prisoner? You have to pass the broom to the prisoner with the broom in this orientation, in the up and down orientation like this. Then the broom will be able to slip in between the bars. That's what's happening. Your scattered light is now in the left and right in all the different angles. They're being blocked. The only thing that's being allowed to pass through is going to be the waves of light that are going to be in the up and down orientation. So when you have these are two filters with the that are having the polymers in the same orientation. Okay, so let me lift those up so you can kind of see. The light is still able to pass between those. Well, imagine that you have a high security prison where they don't want brooms being passed to prisoners because they don't want them to clean their jail cells. Maybe the broom can be used as a weapon or something. So what they do is, in addition to having the bars going up and down, you also have the bars that are going to be going to the left and right. So let's go ahead and draw these polymers. So now the polymers are going to be in this orientation like this. Okay, so now what's coming through is only the waves of light that are in the up and down orientation are going to be coming through. But then it hits the polymers, which are going to block everything except for the waves of light that are going left and right. But we don't have any more waves that are going left and right because all of my left and right waves have been blocked from this first filter. So again, imagine that you're trying to pass the broom. The broom can make it past this first row of bars going up and down, but it's not going to make it past that second block of bars that's going up and down right there. So what happens is the broom's going to get blocked. Okay, if you can imagine that if this is like a magnet, for example, let's say this is the north and south orientation, like the poles, and then we've turned it on its side to the north and south orientation like this. That's going to block all the waves of light. And you can actually see this with the polarized filter. Okay, so these are having the polymers in the same orientation, and then when you rotate the second screen or the second filter, you'll notice that it's going to block the light. Here, the molecules are in the same orientation and allowing only light to travel in the up and down direction, but when you get that second filter, which blocks the left and right, you now are blocking all of your waves of light. So that's polarized filters. Now, another interesting feature of polarized filters is they used these for sunglasses. Because if you remember, your sun is coming to the earth and it's coming with scattered light. Okay, we can also say that this scattered light is unpolarized or it is not polarized. So all of these waves of light are coming down, okay? I'm going to try to draw this in a different orientation. They're coming down to hit the earth. And if it hits the surface of water, sunlight, of course, is going to reflect off of that water. But what's interesting is that when scattered light hits a surface and it reflects off of that surface, it comes to your eye polarized. So the sunlight's coming from the sun in the scattered version, hits the water, and when it reflects back to your eye, here's your eye over here, your eye is going to have polarized light come to it. So a lot of fishermen are aware of this, but what they do is they wear sunglasses. And those sunglasses are going to have a polarized filter on them. So they're going to be polarized lenses. So here's a polarized lens or polarized lenses, which are going to be in front of the eye. So what's going to happen is this polarized lens, very similar to this right here, this has an amazing ability to block the reflection. Let me show this to you. I have my cell phone here, and I'm shining it at an angle towards the window. So I can see the reflection of the window inside of my phone. So if I take the filter like this, okay, watch what happens when I turn this. More light comes through, less light comes through. More light comes through, less light comes through. So we actually don't need two of those filters to block the light. We only need one of these and a reflection to help block the light. So that's how the polarized lenses function, because what it's going to do is this reflection that's coming off of the water is going to get blocked. Right here, the lenses are going to block the polarized reflection. Lens blocks the polarized reflection right here. So what does that enable the fisherman to see? Well, since we've blocked this glaring reflection off of the sun, what we're going to be getting are other light rays, like from the fish, which are not reflecting off the surface of the water, and these are also going to make it into the eye. So the fisherman is going to be able to see the fish. So we can see the fish under the water, even though there's a bright reflection that is coming off of the surface. So these polarized lenses, what they do is they block the reflected light, and so the fisherman actually sees the non-reflected images which are coming directly from the fish underneath the water. That's another useful function for polarized lenses.